And we go then, last day of calculus, right? Final exam is on Monday night. I'm giving nothing new today except for your education. It won't be on the final. I believe it's 7:30 to 9:20 p.m. And what we're going to do is problems just like the practice problems on the practice set on D2L.
Can you move the camera, please?
Oh yeah, I forgot to set the camera up. Yep. Good idea. I see it pointing at me. I forgot to move it. Yep. Oh, you gotta go out and buy her pizza after the semester for keeping me on track here. All right, problems like the practice tests. But what I'm gonna do is change the functions, change the surface, the numbers, all that. But I'll make them similar. So instead of a hyperbolic paraboloid, maybe you'll get an elliptic paraboloid or something. Change functions, the numbers. Go on here now. All right, and then problems like those since the last, well, maybe I shouldn't say something. Problems like those of chapter 15. Including the 1 through 10 on the notes. All right, so chapter 15 from the text, 1 through 10 from the notes I gave, and problems just like those. That's more than enough to do already, but I'm gonna just make all the problems just like that. I'm gonna make this a little shorter than a final. Let's make it about an hour and 15 minutes, about the same length as the midterms. And then you have some time to check your answers. I don't have time to grade anything longer than that. I won't get my exams in time. Probably. So an hour and 15 minutes approximately, and then check your answers. I always miss something on my own exams. The reason I don't check them is I know you guys are gonna get them, and I figure it out as I go. But if I was turning it in, I'd check them. All right. Again, it's open notes, open books, it's email only again. Next semester will be better. It'll be fun. I'd love to see your faces. I'm so sorry I don't get to know you better this semester. I just feel awful with that. Come and say hi next semester. Let me know who you were. You know. All right, so email only, open everything, not everything, because somebody will be creative and come up with something I didn't mean, but open book, notes, computer, but no online tutors on the computer. No people can help, right? Any questions on the final exam? Well, on anything that you want to know, yeah. Okay, yeah, we're gonna go over review questions here shortly then. That was just to see if you had any questions about the final exam itself. Yeah. All right,
I'm confused on like the specified problems like a practice test, and then you made it a point to specify problems like those in chapter 15.
so it's both of these. Some of the problems will be just like the practice test problems. Some will be just like those at chapter 15, including those 1 through 10 out of the notes. So between these, that'll be all of it.
Okay.
If it's something from before chapter 15 that isn't on the practice test, don't study it. You don't need it, except as it applies to these problems. Right? That's plenty to study right there. But I want to make it real similar to these. I may not make the exact wording or word it for the test, but I'll make it the same kind of problems, change the numbers and functions around, and that'll be good. Now, with that said, I did have one more thing I wanted to say just for your education. This will be not for the final. This is probably mostly for math majors. I don't think the engineering majors and science majors are going to need this so much. But there's another form of the surface integrals that we skipped over last time. With the idea that it's not used very much. but it is of some theoretical use in higher mathematics. You won't need it in differential equations. In advanced calculus, you might touch on it briefly, but we just want to mention it. Surface integrals can also be written over parametric surfaces. We wrote it for surfaces z equals f of x, y, right? For those surfaces, we had a formula, right? V equals f of x, y is the surface of a function such as a density function. G, no, we call this one G, didn't we? Z equals G of x, y, of a density function of some sort, f of x, y, z, where not S, say the double integral over the surface sigma of f of x, y, z, the S could be thought of as finding the mass of the surface, right? If this is the density function, f of x, y, z, for a surface that has this equation, this would be the mass, for instance. This is an application. These could be evaluated by taking the double integral over the region of projection R, that's the domain on which this is defined, of f of x, y, z of x, y. Well, we could call it g of x, y, times the infinitesimal surface element here, dz dx squared, where z is equal to g of x, y, so it's dg dx squared. dz dx squared plus dz dy squared plus 1 dA. That's a useful formula for final. If I ask you to do the surface integral, you can use this. Or if it happens to be a closed surface, you could try the divergence theorem to calculate this, right? If it's a flux, I guess I should say. So if it's a surface integral, not a vector surface integral, you use this. And we derive this, at least to a certain extent. We didn't put in all the details. What about the following alternative? Alternatively, some surfaces are given parametrically. Now, I'll just give one short example. For this one, you might write x equals x of uv, y equals y of uv, a function of uv, and z equals z of uv. There's a parametric surface, two parameters, u and v. And if you take this of the function f of x, y, z, this gives you like a density at each point on the surface or something. Or it could be a mass density or a charge density or something else. These were the population density along a hilly region or something, right? Has a surface integral that's similar. And I just want to go through the general picture because we're not doing this. You won't remember all the formulas in between anyway. But the idea is this. You've got in the UV plane some easy patch in the plane. Maybe it's a constant limit point. It doesn't have to be constant, but I'll just draw it that way because that's really what you'd like to do. Here in the UV plane is some domain S. And I have this parametric map. X is a function of UV, Y is a function of UV, Z is a function of UV that takes it into three-dimensional space, X, Y, Z, to some generally curved surface, where each point in the plane is given by these coordinates, right? X of UV, Y of UV, Z of UV. So each point on this in this region, UV, mapped to a point on the surface over here. And you sweep out the surface, then what happens is if you divide up this thing, right, you increment this in U and V, each fixed value of U and each fixed value of V makes some pattern across here, which doesn't necessarily look square or anything. These might meet at extreme angles. But here's curves of fixed U maybe, and here's curves of fixed V, and you get this kind of pattern over here. What is the area of a little tangent plane over one of these patches? Well, if you take the tangent plane up here, its area, if you call it delta A ij, corresponding to the ij square here, not square, rectangle. This surface area, or this tangent plane area, is actually the length of, you'd use the cross product, right, to find the area of a parallelogram. This is a parallelogram, and its area is just dr du cross dr dv delta u times delta v, where r is the vector valued function x of uv, y of uv, z of uv. And you take that cross product, and then you take the limit of the sum of these areas to estimate the surface area. And then if you want an integrand to put a density with it, then you have that the surface integral becomes a limit of the sum of these. And again, this would be at the ij point. And so you sum a bunch of those. So the surface integral, waving my hands a lot, comes by taking the limit of the sum the double integral of f, right? You're going to take the surface integral of f like this, ds. Let's write it. Double integral over sigma f of x, y, z, ds. The surface integral can be evaluated as f evaluated along the parametric surface, x of uv, y of uv, z of uv gives the f at the given point parametrically. And ds becomes replaced by this. It becomes the RDU cross the RDB length times du dv. And there's the last formula for this festival. So this is another alternative way to evaluate these things if you give get a surface given parametrically. So I'm going to do one example of that. And so I don't waste your time. 5 points if you want to send this to me tonight. Extra credit. Basically, if you just turn it in, I'll give you the extra credit. I'm not going to mark it. You're supposed to write down what I do and send it in. And that way you've practiced one, you should get something for it, right? Find the surface area of the unit sphere. And by the way, I should mention, let me move this back for a second. What happens if the parameters u and v are just x and y, right? So actually, maybe this is the xy plane. X equals u and y equals v. Then this just becomes x, y, g of x, y, right? And you get this case right here. This cross product is actually this. This is dr dx cross dr dy, and dA is your dx dy. So it actually becomes this formula when u equals x and v equals y. And so this generalizes our surface area formula that we did over there to these non-rectangular regions because they're in UV space and they transform over parallelograms over the thing. All right, now 5 points extra credit. What's the surface area of the unit sphere? We can write a parametric surface by using spherical coordinates with rho equals 1, right? Spherical coordinates with rho fixed at 1 to sweep out the unit sphere. That means x equals rho cosine theta sine phi, but rho is 1, so it's just x equals cosine theta sine phi, right? Y is rho sine theta sine phi, but rho is 1, so it's y equals sine theta sine phi. And then z is supposed to be rho cosine phi, so now z is just cosine phi since rho is 1. This example is in the book, by the way. Look at it again. These are parametric equations for the unit sphere. Well, we can change this one just to match that one and call this cosine u sine v, sine u sine v. So you can make it u and v that your theta and the theta equals u and phi equals v. And whatever I call that, double star. Double star. Tells us that, well, let's see. dr du becomes replaced by dr d theta. And this is x, y, and z, and r becomes minus sine theta sine phi when I take the derivative of x with respect to theta. The derivative of y is cosine theta sine phi. The derivative of cosine phi is 0 because theta is not there. dr d phi becomes, now cosine theta is held constant. I'm taking partial of sine phi, and I get cosine theta cosine phi. And then y partial with respect to phi is sine theta cosine phi. And then partial cosine phi with respect to phi is minus sine phi. Oops, minus sine phi. So there's the dr d theta and dr d phi. And then you need this area of the parallelogram, dr d theta cross dr d phi. Comes out just to be with a bunch of work, right? It's a determinant. Comes out to be sine phi. So I'll leave out the work since this is just an extra example. If you calculate the cross product of these two and take the length, it comes out to be sine phi. Maybe it's cosine. No, sine phi. Now, I want to leave out the details for this one. But just write this down and send it to me by email, or if you're in class and want, you can leave it with a piece of paper instead. Just do it tonight. People who don't show up can see this later and say, why didn't I come to class? Huh? All right. There's.
Like, we just email it to you?
Yeah, you can email it tonight, or you can give it to me on a piece of paper tonight, whichever one you like. Just from here down. Now, what is the surface area? The surface area is the surface integral of 1, right? dS. Well, according to our prescription double star, this is the r d theta cross the r d phi, d theta d phi. All right, this becomes your ds for this parametric surface. And then this is over the patch r in the theta phi plane. What is the patch in theta phi plane? Well, remember we let theta go from 0 to 2 pi and phi go from 0 to pi to sweep out the unit sphere. So this is the corresponding patch in UV space or theta phi space. I should say over S. I used S over there. Right, S. And so this is the double integral Let's see. Going from 0 to 2 pi, and 0 to pi of sine phi d theta d phi. Well, the integral d theta is just 2 pi. And then I have an integral from 0 to pi of sine phi phi. Right, which I hope I got this right, is 2 pi. Integral of sine phi is minus the cosine of phi. Something here. 0 to pi. Cosine of pi is -1, so I get a minus and minus 1, and then cosine of 0 is 1, I get minus and minus 0. This becomes 2 is the point, and then we get 4 pi, and I'm missing a third here. It's supposed to give me 4 pi over 3. Not sure where I dropped my third at. It might be in here.
Did you have the rho squared sine phi? Oh, well, I guess that's what's the,
Yeah, this is the rho squared sine phi in here, and rho is 1. So this becomes, oh, let's see. Yeah, so this just becomes sine phi. So normally, this would be rho squared sine phi because it's spherical coordinates. Well, we're on the sphere of phi equal, rho equals 1, so it becomes sine phi. That's why I wrote that down there. So I'm missing my 1/3.
ten bonus points if we find the 1/3.
It's in the book. All you have to do is read the example. I just can't remember. I don't want to work it out right now, but it should be 4 pi over 3. I'll leave it like that. But you can see the book, 4 pi over 3. It's in the main part of the section. And I've forgotten where I left my outline. I don't see anything wrong with that. All right.
Do you know what section this would be? Surface intervals like 15.5?
It's the one called surface integrals. It's right before the divergence theorem. So it's probably, anyway, I don't remember the number. All right, so let's leave that there. I don't want to eat up too much of your time here. There's plenty of time. Rather than try and find the 1/3.
Credit quiz at the first of the year too, is that still
Yeah, you still got 10 points from that. So,
floating around
so you
somewhere?
could have 15 total if you turn this in. All right. All right, so now let's look at the final exam here, and I'll worry about the details. Let's say, look at the text and you can see what it's 3. There was a problem you wanted to look at, is that right? Okay. Online, feel free to ask whatever questions you want to. I'm just gonna field questions and throw a few of them that I think you should look at too.
Two, five,
Which one?
4.
Okay. Let's look at 24, and I gotta move the camera.
Other questions? Oh, no.
Okay. 24 says this then, use Green's theorem. We'll say by Green's theorem. Find the vector line integral f dot dr. Green's theorem only applies to closed curves. Theorem itself is for counterclockwise, but if it's clockwise, you just put a minus in it. If for an integral around a curve C1. If you're given that the integral around a curve C2 is 40. Over the following region, it's a region with holes in it, right? Green's theorem doesn't apply to the regions with holes. So what am I thinking here? Green's theorem for multiply connected regions, right? We said right at the end of the Green's theorem stuff, if you have one or more holes in the region, you can take the sum of the integrals going counterclockwise around the outside and clockwise around the inside, and that adds up to the double integral dt dx minus df dy also. So that'll be Green's theorem for multiply connected regions. So if this one goes counterclockwise and this one goes clockwise, and suppose this is a circle of radius 1, and this is a, that number's blotted out on the bottom. The word below came over it. That's not good. So this is a 3. I was thinking it was a 5, but it might be a 6. Yeah. Oh, I can't believe that. I didn't notice it. Let's suppose it's a 6 like you think, because I can't read it at all. And suppose it's this region. I might get a different answer than the back if this is the wrong number. How do I use Green's theorem to find the line integral over C1, the inside curve, going clockwise, if the integral over C2 going counterclockwise is 40? And I also know, this is given, that the dx minus df dy of the, I used F2 and F1. This is the book's notation, G and F, is equal to 2, where F, the vector field, is F plus G. J, we don't know what F and G are, but this is the difference in the partial derivatives. Right? How can I do that one? Well, it is Green's theorem, right? Green's theorem says that if you sum the ones going counterclockwise and clockwise, so you take integral around C1, f dot dr, plus the integral around C2, f dot dr. This one going counterclockwise and this one going clockwise. It should add up to double integral of dg dx minus df dy. dA over the region R in the plane. Well, this side is easy to compute, right? Because we're given that this difference in partial derivatives is 2. So this is just the double integral of the region of 2, which is what? Pull the 2 out, and it's 2 times double integral R dA, which is
Rectangle or for the circle?
for the shaded region between the rectangle, inside the rectangle, outside the circle. Take the area of the rectangle, 6 times 3, minus the area of the circle, pi r squared is pi times 1 squared. And so it's 18 minus pi, all times 2 is 36 minus 2 pi. So that's the right side. Now I'm also given that the integral around C2 is 40. And I'm asked to find the integral around C1. Hence, the integral that we want, integral counterclockwise around C1 f dot dr plus 40 equals 36 minus 2 pi is then equal to 36 minus 2 pi minus 40 is minus 4 minus 2 pi. Is that the answer in the back? If it's not, then I've got the wrong dimensions here. Oh, that's it. Okay, hey, you did read it right. Hey, thank you. I can't even see that at all anymore. All right, so there's Green's theorem for multiply connected regions. I want you to see that because some engineers have to do these kind of integrals.
Wait, from that step where you had 36 minus 2 pi, why'd you subtract 40?
Oh, I said this integral plus 40 equals 36 minus 2 pi. And so I subtracted 40 from each side. Let's write it this way. The line integral f dot dr, we're given this integral is 40, so plus 40 equals the right side 36 minus 2 pi. Right? That's what this is. This integral plus 40 equals 36 minus 2 pi. And then I subtract 40 from both sides. So I said the integral C1 f dot dr, therefore subtracting 40 is 36 minus 2 pi minus 40 is this one. I was afraid that was going to happen when I wrote that. All right. Any others giving a lot of trouble?
Number 6.
Okay. Okay, use the coordinate transformation. So parametric equations in the plane, which we did cover. We didn't do surfaces till today. Number 6 says this. Find the double integral x squared minus y squared dA over the region R, where it's a rectangular region enclosed by the lines x plus y equals 0. That's y equals minus x. That's this one. X plus y equals 1. That's the same thing with intercept y equals 1. Parallel line. And if you rewrite this, this is equivalently y equals minus x plus 1. So it's slope minus 1 and y-intercept 1. You can sketch it through 1 and slope minus 1. It goes through this one. Just to say what it looks like. And then the other two lines, yeah, this is a good one to ask. This is a tricky one. X minus y equals 1. That's y equals x plus 1. So that's this one. X minus y equals 1. How do I know that? I plot 2 points, or I can rewrite it like this one. Wait a minute.
Can you translate that line down to y equals x minus 1?
Yeah, it should be down here. Yep. X minus y equals 1. If you rewrite that as y equals x minus 1, then it's slope m equals 1, y-intercept equals minus 1. So I put it down here through minus 1 and make it plus slope plus 1, and it goes through this one. All right, and then the last one is x minus y equals 4. That's the same slope with y-intercept 4, so it goes up here to 4. And it goes down like this. Here's x minus y equals 4. Also known as y equals x minus 4, slope 1 and y-intercept. So here's the rectangle. What a terrible integral. Can you imagine trying to do this in x, y coordinates? What would I do? I'd say, well, gee, I go from here to here with this on top and this on bottom. Then I got to figure the equation here. I go from here to here with this on top and this on bottom. Then I go from here to here with this on top and this on bottom. 3 type 1 regions.
The other line, yeah. So the intercept is -4.
Did I mess that up? Oh, yeah. Oops. Yep. Again. Same kind of concept, though. I appreciate that. So y-intercept is -4. Looks like that. This one. All right, so there's our region. And it's a rectangle, actually, if I draw it correctly. Top end here. How can I do that instead of breaking up all those things? I can make a transformation of variables. I can let, I wrote it in here, right, because I don't want to make this where you have to figure it out. You can figure it out, but it's too much for the test. Let u equal x plus y, p equal x minus y. Why would I want to do that? All right. Well, what that does is it turns these diagonal lines into horizontal lines. That's the main thing. And so you'll get a rectangle, a vertical and horizontal rectangle in the UV plane. Furthermore, the integrand that becomes u times v. So this will make an easy integrand and easy limits, and I won't have to break it up into 3 integrals anymore. That's the idea what these transformation variables can do for you. So we'll say now that this double integral, according to what we said, is the double integral over u and v, which is some region S that maps into this from UV space. Transformation phi, a map, which is this. It's u equals x plus y and v equals x minus y, the inverse of that actually. And there's some region in here, whatever it is, S. And so we're going to integrate over that one instead of over this one, R. And then we'll write this as, well, let's see, this is x plus y times x minus y. So it's actually equal to u times v. Let's see, which one was u? Which one was v? U times v. I can write this as uv. And then you need to hear the magnification factor, right? Because each unit area here is mapped into a different size area here by this magnification, which is the Jacobian that we write dxy d duv, and then you have to take the absolute value because it's plus or minus the magnification actually. Absolute value gives the magnification. And then du dv. So you can do this instead. That was our theorem for change of variables in the plane. Now, how do I calculate that? Well, remember this dxy duv, we also call J for the Jacobian. We can calculate if we know x and y is a function of u and v, right? dxy duv, the Jacobian. This notation means x du, x dv, y du, y dv, right? Determinant. So let's see, I need x and y as function of u and v. So I'm going to rewrite this. V equals x minus y. And I can, since these are linear equations, it's easy to solve these. Sometimes nonlinear equations, it's hard to solve them to get the inverse. But this one I can solve since it's a linear equation. I can add these. If I call these 1 and 2, I can take 1 plus 2 to make the y's cancel out and get u plus v equals 2x, right? And then if I subtract them, 1 minus 2, and generally add a multiple of 1 to a multiple of the other and eliminate a variable. You call it an elimination if you take limits. This one minus this one tells you that u minus v is equal to 2y. Evidently, x equals 1/2 u plus 1/2 v. Y equals 1/2 u minus 1/2 v. This is the transformation phi of uv equals x of uv, y of uv, the map that takes x uv coordinates into the xy plane. Phi goes this way, uv to xy. And they give it that letter phi sometimes. But the point is the Jacobian is just this determinant of partial derivative. So dx du is apparently 1/2 plus 0, right? dx dv is 1/2 plus 0. dy du is 1/2 minus 0. dy dv is 0 minus 1/2. So there's the Jacobian, is 1/2 times 1/2 is 1/4, minus this diagonal, 1/2 times 1/2. Oops, I'm sorry, this was minus 1/4. 1/2 times minus 1/2 is minus 1/4. that diagonal, minus this diagonal is minus another quarter, is minus a half. What happens if you get 0? It's a bad transformation, the theorem fails. What happens is it will map like the plane region into a line somewhere or something. It'll have a singularity in it where it's not a one-to-one transformation. You can't necessarily invert it. So the theorem applies when the Jacobian's not 0 on the region. In this case, it's minus a half everywhere, so it's not 0 anywhere. It works, so this is good. And what that means is you take an absolute value of a half here, and I need to integrate over the plane region S, uv times a half du dv. It's over, don't I? I got it, I guess. I think. Okay. And now what are the integration endpoints? You have to figure what they are. If you take you remember these linear transformations where u equals ax plus by, v equals cx plus dy, it just maps lines, parallel lines to parallel lines. So this rectangle, special case of parallelogram, will map to a parallelogram in UV space also. And I noticed that if I take this point 1, 0, what does that go to? X equals 1, y equals 0. I get u equals 1 plus 0 equals 1. And v equals 1 minus 0 equals 1. So the point 1, 1 is right here. Oops, I'm off the screen. Good. So point 1, 1 corresponds to this point right here. This point right here. He takes that one to that one. And then we can take this point right here, which where is it? If I intersect x minus y equals 0 with x minus y equals. This was x plus y equals 0. I'm pretty sure. Yeah. Intersect x plus y equals 0 with x minus y equals 4. I get x equals 4. No. I get x equals 2 and y equals negative 2. Yeah. So I get the x equals 2, y equals negative 2. Where these intersect, right? So I get 2 plus negative 2 is 0. 2 plus minus negative 2 is 4. So that's going to give me, apparently, I'm going to being the case 2, negative 2. So I've got 1, 1 for the 1 point. And then 2, negative 2. And then the other points, I think, line up in a rectangle. That was the idea of this. If I take this point here, oh, wait a minute, that was that point here, wasn't it? X plus y equals 0. Oh, no, that was that one. X plus y equals 0 and x minus 1 equals 4. So x plus y equals 0 and x minus y equals 1.
So these 4 points on the region R, are you plugging those into what u and v are equal to the beginning of the problem, or the let?
Yeah, I'm putting the x, y coordinates here into the equations 1 and 2 and calculating what u and v are at the corner. So the intersection of these two is that x plus y is where x minus y equals 1 intersects x plus y equals 0. So it has to satisfy both those equations at this corner. And if I add those together, I get 2x equals 1. Apparently, oh, that doesn't, this is supposed to be a rectangle, I thought. Mistake somewhere.
The 2, negative 2, when you plug it in, should give you 0, 4, I think. So I just got.
So I got the wrong point here. This says x equals a half, and then if I put, and then y equals a half, y equals minus a half.
Oh, you're letting U and V equal the point you plugged in? You're not just like plugging in X and Y to get,
I'm finding X, Y at each corner and then plugging it in to get U and V out of these equations.
okay.
If X is a half and Y is minus a half, I get 0. Oh, there we go, 0, 1. So it should be, this one was, so that one gave that. Now, if I put X equals a half, Y equals minus a half, the other corner here where these intersect, this is the point 1/2 minus 1/2, just by finding the intersection. I plug that in here, 1/2 plus minus a half is U equals 0. And the V is a half minus a negative a half, V equals 1. There we go, that's what it should be getting. And so I get the point 0, 1. That's this one. Now this one was 2 minus 2, right? So U should be 0 and V should be 4. Yeah, and so this one gives me 0, 4. Was 1, 0, right? Yeah. This was a half minus a half. This one here is probably wrong. X minus Y equals 0. No, that's not the right one. X plus Y equals 0, intersecting X minus Y equals 4. Let's try that one. So this intersection here, X plus Y equals 0, intersecting X minus Y equals 4. At that point, if I add these two down, it gives me 2x, or so X equals 2. I put it in here, I get Y equals minus 2. I get the point 2 minus 2. Oh, yeah, okay. X equals 2 and Y equals minus 2. And now you put that in here, and I get 2 minus 2 is 0, so I get U equals 0, and 2 minus a minus 2 is 4, so I get the point 0, 4. So 0, 4, this implies U equals 0, V equals 4. And now I have 3 points. Here's the 3 points. They're on this parallelogram. I know where the last one is automatically. It has to be right here, so that these two lines are parallel and these two are parallel. It has to be at the point 1, 4. So this is the region S by taking, by figuring out what these points correspond to in the UV plane, the corner points. So now I know U integrates from 0 to 1, V integrates from 1 to 4. By seeing what the region S is, whose images are here under the. Now I've got it. It's easy, right? This separates of the product of two integrals, the integral from 1 to 4 of V dV times the integral from 0 to 1 of U du, all times a half. Right? So this is 1/2 V squared over 2, plug in 4 and 1, take the difference, times U squared over 2, plug in 1 and 0 and take the difference. Evidently, I get 1/4 from this one. Let's see. Oh, that's so easy. 1/4 times 4 squared is 4. Top. And then 1/4 times 1 on the bottom. That's what I get at this one. 4 minus a fourth. Then I multiply it by this one, 1/2 minus 0. Evidently, I get 15 fourths times a half is 15 eighths. Hopefully that looks like the back.
Yeah, I think that was the answer. Yeah, that's the answer.
Good deal. Okay, so there's how you do that problem. find the region here. I'm gonna make it a rectangle so it's easier. That's the purpose of this transformation, is to make an easier region so you can do the integration just with this Jacobian stuff in. All this is on here online, right? There we go. Okay. That was a good question. The hard one.
Where did the 1/2 go?
Oh, it's this 1/2 here. And then this is v squared over 2, plug in formula and take the difference. This is u squared over 2.
Oh,
Here's what I want to ask you. There's a good chance I'll ask you this on the exam. I'll bet you can guess why if you really think hard about it. I told you how these machines are making integration so easy, right? My TI-89 calculator does all these double and triple integrals. And so does Symbolab, and with steps in between. And you get more information if you pay them some money. It's not very much. Or you can go to Wolfram Alpha and give you the answer without the steps, or you can go to the integral calculator and do some of these. I don't know if it does multiple integrals. I can't. May not. But what am I going to do to make sure you know how to do multiple integrals unless I ask you questions like this? I guess this needs over far enough again. Or maybe I'll ask you one like this. 16, because this comes up a lot in practice, and you pass your class by doing the Wolfram Alpha or something all the way through your tests, and then you get to your engineering job and you have this integral. What's the integral from 0 to 1? Integral from 0 to square root 1 minus x squared, 3xy, y dx, and the calculator fails. Why do you think it failed? It probably failed. I'm not sure on this one. Since calculators only look at the integral itself, they aren't clever, right? There's a lot of integrals where I've got a book this thick that I bought as a graduate student because my quantum mechanics teacher was giving us all these terrible integrals, and I had to look them up. There was no internet in those days. And you guys are so much smarter now. I'm a lot smarter than I was as a graduate student. But those clever techniques are all compiled into big books, and the integral calculators know some of them, but from what I've seen, they use a little different techniques than you usually do by hand. So some of these come out interesting, like, well, let me not go off on a tangent here, but I don't know if it's clever enough, probably not, to do this one. But what you can do, and what the instructions say, and what I'm likely to be in the test, is convert to polar coordinates, because I noticed that this will look nicer in polar coordinates. And I've suggested first sketch and convert to polar coordinates. That's the way you convert these. All right, you notice that it looks like it might be nicer in polar coordinates, and so you try it. What do I do with polar coordinates? Well, I first sketch the region. What is this curve here? This is the top curve, right? This is a what we call a type 1 region. It goes from the minimum x to the maximum x. A bottom curve, y equals 0, and a top curve, y equals square root 1 minus x squared. So I plot all those things, x from 0 to 1. And then, what is this one? Y equals square root 1 minus x squared. This is where the human comes in and says, well, square both sides, that's kind of clever. And then I recognize by adding x squared over, so it might be clever enough to do this because it's a very common problem, but there's lots of problems like this it won't do. X squared plus y squared equals 1, that's the unit circle, right? So I know it looks like this. But I only draw it for x between 0 and 1, and this is only the positive square root, so I only graph the top half, right? When I square both sides, I have to also stipulate for it to be an equivalent equation, the y has to be non-negative. Now these are equivalent. And then it's equivalently the unit circle, top half, or the unit semicircle. So it's unit semicircle, and then I restrict it to x between 0 and 1. I think probably the calculator is not that clever to take half the unit circle, a quarter of the unit circle. So there's my region R, if you like. I can say this is the double integral over the region R of 3xy dA, right? I'll write it like that as an intermediate step. You don't have to. Now, how do I get it in polar coordinates? Remember that?
X equals R cosine theta.
Yeah, I write it as a simple polar region, which means it has to go between two rays. Theta equals alpha, in this case 0, and theta equals the maximum angle. Theta equals beta, in this case pi over 2. You notice it goes between two rays. It is a simple polar region. And then I have an outside curve, r equals 1, since it's a unit circle. And an inside curve, r equals 0, this is just a point. And now I have a simple polar region, the book calls it, I think. Something like that. And this is now equal to the double integral over the simple polar region, r going from 0 to 1, theta going from 0 to pi over 2, of the same integrand with x and y written as functions of r and theta. So x gets replaced, as you said, with r cosine theta, y with r sine theta, and then dy dx gets replaced with r dr d theta. Don't forget that r, that's going to be more than 1 point off, probably more than 2 points off. So that's what it looks like. Now I can separate it. The 3 comes out. And because these are constant endpoints, I mean, it's just the argument before. You write as a function of theta times a function of r, and these are constant endpoints. So you can pull the inside integral out and rewrite it as integral from 0 to pi over 2 of the theta stuff, sine theta, cosine theta. Theta times the integral of r stuff, r cubed dr. And probably the calculators don't do this, so this is why you probably get this on the final, right? Something like this. Now you can do those by hand, and they aren't too bad, right? The calculator can do these once you get to here. I'll probably use that, but show your steps.
R is from 0 to 1.
Oh, yeah, 0 to 1. So how do I integrate this? I can substitute u equals sine theta and d equals cosine theta d theta, or maybe it's easier just to write this by the double angle identity is 1/2 sine of 2 theta, integrate that, right? Integral of 1/2 sine 2 theta is 1/2 minus cosine theta over 2. And then times the 1/2 gives minus cosine 2 theta over 4. I'm going to plug in 0 and pi over 2. All right, and then times r to the 4th over 4, plug in 0 and 1. But at this point, you should definitely check your answers with one of those calculators, because it will do these single integrals wonderfully, right? These are easy integrals. Check these by calculator if you have time. All right, so cosine, you got 3 times minus the cosine of twice pi over 2 is pi, or minus the cosine of 0 times 1/4. Well, it looks like 3/4. This is 1/4. All right, because cosine pi is -1. Minus a minus 1/4 is plus 1/4. So all that comes out to be 1/2. 3/4 times 1/2 be 3/8 for that one. That's what it says in the back there. I forgot what number that is.
Yeah, 3/8 is what you have in there.
Okay. 16, yeah. Okay. So there's how you do that one, right? You have to be clever, be a human and convert it. And we can get harder ones than that you can still do easily with the machine. I may try these in the machine, who knows, and see if it can do it. But they're good at single integrals. So it's my calculator, my TI-89 will do multiple integrals, but it's not clever enough to switch coordinate systems. So those are good candidates for the finals where I make you be a human, right? Just copy off the machine. Calculus 2 is getting just terrible. Those calculators can do all their integration techniques. People don't want to learn the techniques anymore. Then they get into trouble in calculus 3 and 4 because see they need to do this stuff from calculus 2 and they can't. And all you gotta do is get a little bit theoretical, put enough variables in there, put integrals with cases. Here's an integral. Try this on symbol lab. Integral 0 to pi square root 1 plus cosine theta. This is actually very easy to integral. I'm surprised it doesn't do it. It will do it if you take off the endpoints, I think. It'll give you an antiderivative. But because this square root integral square root of 1 plus cosine theta has cases where it switches to positive and negative. It seems to have trouble with it, but if you just replace this with a half angle of cosine squared 1/2 theta, since you're between 0 and pi, it's positive. And then you can integrate it, cosine squared, cosine 1/2 theta. You can integrate cosine 1/2 theta and get 1/2 sine of 1/2 theta. And so it's pretty easy, but if you good ones with cases, they have trouble with it still times. So even if you do use the calculator, there are some that will occasionally give you a problem. All right. Anybody online got a problem you want to look at? Have you been trying these? Do the chain rule,
Can you do number 14?
23?
So 23 looks pretty well.
Okay. Oh, the area of the ellipse. Actually, we did that one last time. I think, maybe not last time. Let me look at it here. We had a formula. We did Green's theorem that says you can calculate the area enclosed inside a region by taking integral x dy around the closed curve counterclockwise that it's its boundary. Right, and there's a neat instrument called a planimeter, I think it is, where if you take this thing that sits on a table, it's a mechanical device, and you trace out a figure, it can tell you how much area is inside. And it can use this formula to do it. So, but that's what this formula says. We proved this actually from Green's theorem. It's a result. If you have a region A of this region, you can calculate by integrating along the boundary x dy. Or you can do it by minus the integral y dx, or you can take a weighted averages, 1/2 this one, 1/2 this one, or 2/3 and 1/3 and add them together. People do that actually in practice, is why I mentioned that. But suppose we do this one, 1/2 x dy, we do it for the specific case of the ellipse. 23, x squared over a squared plus y squared over b squared equals 1. What do? I write this parametrically in order to do this curve, because this is integral from a to b. Remember how to do these? If it's a function of x and y dx plus a function of x and y dy, right? You treat dx and dy as dx dt dt and dy dt dt, right? This is x dy dt dt, and that's how you evaluate those line integrals. All right. So I need to write this parametric curve if I let x equal a cosine t, y equal b sine t, then x squared over a squared will be cosine squared, y squared over b squared will be sine squared, and this will be sine squared plus cosine squared equals 1. So this parametric curve sweeps out this ellipse, and if you think about it a little harder, I'll wave my hands because it's technical, but you don't want to spend too much time on it. T goes from 0 to 2 pi, you sweep that out. So here's a parametric curve that sweeps out the ellipse once. So I can let this be an integral from 0 to 2 pi of x, which is a cosine t, times dy dt, which is the derivative b sine t is b cosine t, dt. This integral gives the area inside the ellipse with semi-axes A and B. This area, that's what we're finding for this problem. That's easy. A and B are constants, right? That's the idea of the ellipse. So it says AB, you can pull it out, integral from 0 to 2 pi, cosine squared t dt, and we know how to integrate that one with the half angle identity, for instance. It's AB, integral from 0 to 2 pi. We write cosine 2t, cosine squared 2t is 1 plus cosine 2t over 2. Screen, yeah. And now I can integrate this. This is AB times 1/2 t plus 1/4 sine 2t, plug in 0 and 2 pi. The sine at the end point is 0, so we drop that out. And we have AB times 1/2 2 pi, and we plug in 2 pi here and 0. Oh, it's just pi AB. There's the area of the ellipse. And a special case when A approaches B, you get a circle, right? Pi r squared, right? That agrees with the circle area you've seen before. Is there a question online? I think somebody started to ask. Maybe it was that one. Okay. Can you do like number 20? We haven't looked at that in a long time. Find the critical points and use the second derivative test to find the relative minima and maxima and saddle points. Or Stokes theorem. Oh, I knew that was coming in, so you shouldn't have come to class tonight. You gotta drive home with that now. All right.
I like to see the Stokes theorem.
Okay, let's try Stokes theorem number 14. Flip the thing over. On 14, I want to evaluate the line integral f dot dr. If f of x, y, z I minus xj plus yk. And c is the unit disk. Reverse counterclockwise. How can I do that by Stokes theorem? The easiest way is to kind of take it easy on yourself and do the plane region with that boundary. Then it just degenerates to Green's theorem. Green's theorem is a special case of Stokes theorem. Or you make it hard on yourself and make some other surface that bounds the region. But Stokes theorem says that this is equal to the double integral over the surface that has that boundary of curl f dot n ds. Or we'll take the upward normal n. So the easiest way is to say, well, let's use the plane region, and then you can just fudge a little and say it's Green's theorem if you want. But there's R and here's C. If R is the unit disk, then let's calculate curl of f. Curl of f is I, j, k, ddx, ddy, ddz for del. And then f1, f2, f3 is 1 minus xy. What is this curl? Well, it's I times dy of y, maybe I should write it out, dy dy minus dz dx, minus ddz of minus x. This one with this one minus this one with this one. Or then minus j times wipe out its Roman column, ddx of y minus ddz of 1. And plus k, wipe out its column and row, ddx of minus x minus ddy of 1. There we go. So dy is 1, and this one's 0, so it's 1i. This one is 0, right? Partial of y with respect to x minus partial of a constant is 0, so it's no j, plus k times minus 1 minus 0. So it's I minus k. That's the curl. So I'll put that in, say this is,
This is
I mean, this is, go ahead, yeah.
So on, when you have the I, it says dy, oh, minus, negative, like d negative x, dz. Oh, that's dz, I think that's a dx. Okay, never mind. Got that.
Okay. And then the normal vector, what's the normal to this surface? You can be pretty sneaky. Since I'm picking it to be the disk in the plane here, this will be r. What is the normal vector? Unit normal, upward. Yeah, it's just k, right? 0, 0, 1, if you like. Well, that's the easy one. If you pick it to be the, like an elliptic parabola, then it's a harder. Now, let's pick the easy one. So this will be the double integral over the surface of 1, 0, minus 1. Curl. Dot n is 0, 0, 1. S is just the double integral over the surface of -1, right? 1 times 0 plus 0 times 0 plus -1 times 1, -1. So it looks like a capital S. ds. So it's actually minus the double integral over the disk, sigma, ds. Well, what's double integral ds? That's the surface area, right? So it's minus the surface area of the disk, which is pi r squared. Pi times its unit circle, 1 squared, so the answer ought to be minus pi. So I did that the easy way, rather than evaluating the integral, I just know it's the area of the surface of this pi for it.
Can we do that, even if it, like the instructions say to use some integral, but the shape is an easy shape that we can just get the area? And we just,
Do what the instructions say. So if I say use this surface, then use it.
Okay.
But here I didn't specify the surface, so I picked the easiest one. Sure that looks right. I think it is. Yeah, that's right. We got about 1 minute. You got a 1 minute problem, anybody?
Like easy to find like that.
Oh, yeah, if you want the upward normal, that's a good question. You take minus dz dx minus dz dy 1 is the upward normal. And then if you take the unit normal, it's just that one divided by its length. You can compute the normal that way.
Upward normal. Huh?
Well, there's two normals. If you have a surface, z equals f of xy. Because z is a function of xy, there's one that has one normal that have a positive z component, and one normal that have a negative z component. So this is the upward normal n as I wrote it. The other one is just minus n. That's the downward normal. So you take dz dx, dz dy minus 1 is the downward one if you want coming out downward. That's a good question too. See, you guys got to ask more questions. You'll learn a lot more. All right. Unfortunately, we're out of time. Till next semester, right? Thank you very much for coming in. It's been a pleasure doing this class with you guys. I love this material. I hope you found a lot of fun in it and get to use it in all your science and math and engineering classes here. Come see me if you have questions. If you want to stay a little after his last day and answer some of the other questions down here. Thank you online for coming in.